Hello everyone, welcome to Sai Tutorials Jamkandi. Here 10th class Kannada medium, math, science, English as well as English medium. Regular classes as well as online classes are available in this tutorial. So I kindly request you to subscribe our channel. The second session of physics for 12th standard is electric charges and fields. We have discussed in the earlier classes the basic concept related to charges and the types of charges and methods of charging and some other properties. So let us discuss in today's class about fundamental properties of charges. See, let us discuss about fundamental properties of charges. See, the charge is conserved. When it will be conserved? Quantity. What do you mean by conserved? The quantity, the net of charge in an isolated system remains constant. See, the first property, the first and foremost property that comes under the properties of charges is charge is conserved. What do you mean by conserved then? See, the algebraic sum of total charges. The algebraic sum of total charges or the net charge of in an isolated system remains constant. In an isolated system, the algebraic sum of the total charge present in the system is constant. So that is in the other way, we can also say that the charge can neither be created nor be destroyed. See, this is nothing but this is the charge is conserved. This is nothing but the quantity, the net of charge in an isolated system remains constant. That is, charge can neither be created nor be destroyed. Charge, that is, neither be created neither be created created nor be destroyed. See, no gain, no loss, which is nothing but no gain, no loss. Here it can be transferred in the sense it can be transferred from one body to the another body. Suppose let us take an example glass and silk cloth. Okay, let us take an example glass and silk cloth. Silk cloth. See, the algebra, I have said that the charge can neither be created nor be destroyed, but it can be transferred from one body to another body. If you take an example, glass and rod, I have plus 3 of, because by losing an electron, it will become positive charge. In the same way, the glass have 3 charges. I mean, the plus 3 charges. But whereas in the silk, it must be minus 3 because these to be balanced each other, where the charge is neither be created nor be destroyed, which is nothing but the charge is conserved. This property is related to the properties of charges. Have you got this, dear students? The algebraic sum or the quantity, the net charge of charge in an isolated system remains constant, or you can also say that the charge can neither be created nor be destroyed, but it can be transferred from one body to another body. This is called as the conservation of charge. This is called as conservation of charge. The second property, when when we come to the second property, that is charge is quantized. What do you mean by quantized then? Here, the charge on any particle is an integral multiple of the fundamental unit of a charge. Okay, it is a integral multiple. What do you mean by integral multiple then? See, the unit of charge E, namely the charge on an electron or a proton. It may be an electron or it may be a proton. Here, it is denoted by the quantization of charge is denoted by Q is equal to plus or minus Ne. I have said that integral multiple of fundamental unit of charge E. See, here n is the number. Okay, here n is the number of charges. Here E is the charge value, the value of the charge. So n is equal to is an integer, that is 1 2 3 4 up to so on, and E is equal to 1.6 into 10 to the power of minus 19 coulomb. See, the protons and neutrons are made up of quarks. Okay, the protons and neutrons are made up of quarks with the fractional values of E. What it is? With the fractional values of E. See, while coming to the integral multiple of the fundamental unit, let us take an example. Let us consider an example. Suppose Q is equal to, they have denoted as, suppose Q is equal to, it may be plus or minus 1 electron. Am I right? Plus or minus 2 electron, plus or minus 3 electron, and so on. Okay, this is nothing but the integral multiple. The integral multiple. Here n denotes the integral multiple of a fundamental unit of charge. Here charge value is same, but the number of charges is different, but the charge value is similar. It may be 1e or 2e or 3e up to so on. Therefore, charge is quantized, or the total charge on any body is integral multiple of a charge on electron. This is called as quantization of charge, or a charge is quantized. Then we will say that charge is quantized. So, dear students, the first property, that is charge is conserved, and second property, that is charge is quantized. When coming to the protons and neutrons are made up of quarks, okay, with a fractional values, not a integral multiples. It will made up of, it is made up of fractional values of electron. It may be Q is equal to quark. Here the fractional values are Q is equal to it may be plus or minus E by 3. Is it in the fractional values, right? Is it in the fraction values? And plus or minus, whether it may be 2e by 3. These are called as fractional values. So, up to so on. See, the protons, and if the protons and neutrons are made up of quarks whose fractional with the fractional values, this must be in a fractional values. However, quarks do not occur in the free state. Why it will be in the fractional values? Because quarks do not occur in the free state. This is all about the quantization of the charge. This is all about the quantization of the charge. And the next property, and coming to the next property, that is charge is invariant. That is charge is invariant. See, we know that mass has, it may be mass is variant, okay, and length is also variant, time is also variant, but charge on a body is independent of the state of the motion. Okay, it is independent of the state of the motion. Here what will happen, uh, suppose let us take it as mass, which is in the rest mass. Okay, let us consider the mass, rest mass, that is m naught, whose value is equal to m naught. But in the mass is invariant, but mass is variant, charge is invariant. Why? The charge cannot exist without mass, but mass can exist without charge. Why? Because but mass is variant and charge is invariant. Why? Because charge cannot exist. Because charge cannot exist without mass, but mass can exist without charge. This is why mass is variant. This is why mass is variant, but charge is invariant because it can't live without mass. That's why it is invariant. And also charge on any body is independent of the state of motion. Okay, it is independent of the state of motion. Next, charge is invariant is okay. And next property, that is charge is a scalar and it is additive. Okay, charge is a scalar quantity. In the earlier class, I have said you that charge is a scalar quantity. What do you mean by scalar then? Which is having only magnitude but has no any direction. Such a property are related to the charge, the properties of the charge. So, charge is a scalar quantity, and another word is there, that is additive. Okay, another word, that is additive. So see the addition. Okay, additive, the word itself indicates that additive means addition or a sum. Addition. See, if a system, let us consider it is a system. If a system contains a number of point charges, here a system contains a number of point charges, the total charge on the system is equal to the algebraic sum of the all charges present in the system. The algebraic sum of the all charges present in the system. See, the charge is additive. When it will be additive? If a system, okay, if a system contains a number of point charges, the total charge on the system is equal to the algebraic sum of the charges present in the system. Sum of the all charges, whatever the charges are present in the system, those are going to be sum. Okay, the algebraic sum of all the charges present in this system. Say, let us consider an example. Suppose, let us consider it is a queue system. Let us consider it is a queue system. Then, if I have the number of charges like Q1, next minus Q2, plus Q3, minus Q4, in this sense, okay, in this sense I have charges. So, the additive property, charge is having the additive property, then the Q system is going to be Q1 plus into minus, minus Q2 plus Q3 minus Q4, so up to so on. This is the additive property of the charge. Have you got this? This is the additive property of a charge. See, if a system contains a number of point charges, the total charge on the system is equal to the algebraic sum of all the charges present in the system. Algebraic sum of all the charges present in the system. So we have considered in the system, the charges present in the system are Q1 minus Q2 plus Q3 minus Q4 up to so on. The additive property, the charges are going to add each other. Then the property is nothing but the addition. Okay. I think you have got this. And next property is like charges repel each other and unlike charges attract each other. Okay. The property that is present here is like charges repel each other. Let me tell you. Suppose, let us consider the like charges, like those two charges are positive only. Two charges are positive only, then they are going to repel, not attract. They are going to repel. Why those two charges are going to repel? Because those two charges are like charges. Like charges means the same charges. If the two charges are present or kept side by side, then they are going to repel, not attract. Suppose if you take the opposite charges like plus and minus, they are going to attract each other. Why they are going to attract each other? They are going to attract each other because those two charges are unlike charges. Those two charges are unlike charges. They are not similar. Have you seen this? See here, this is it is plus charge and it is minus charge. So those two charges are different. Okay, that's why they are going to attract each other. While if you consider the two positive charges, well kept side by side, they are going to repel each other, not attract each other. So if you presented the two charges, that is positive charge and negative charge, but they are going to attract each other. This is the another property of the charges. This is the another property of charges. So dear students, these are all about the fundamental properties of charges. This is all about the fundamental properties of charges. Let me have a small discussion about the quantization of charges or the number of charges. How will you calculate the number of charges? Let us discuss. Suppose I have Q is equal to 1 coulomb. Let us consider Q is equal to 1 coulomb, and what how do you calculate the number of charges then? N is equal to how much? N denotes the number of charges. Then how do you calculate? We know the formula, that is Q is equal to Ne. Is it? Is it right or not? Yes. N is equal. Then N will become, just a second. N will become Q by E. Then what is the value of Q? 1 coulomb divided by, what is the value of charge? Electron. 1.6 into 10 to the power of minus 19 coulomb. Okay, then what is the value of 1 divided by 1.6 into 10 to the power of minus 19 coulomb? It is going to be, see, without calculator you can also calculate this. How do you calculate then? See, here one is there, right? Let us consider it as 10. Okay, it is 10, and it will become 16 into, if I consider this 10 to the power of minus 9 to above, it will go like 10 to the power of minus plus 18, because you have taken it as 10. How did I take this? By dividing and multiplying 10 on both sides. So by this I have considered this. Then you can easily calculate this number, which is equal to 6.25 into 10 to the power of 8 into 10 to the power of 8. This is how we can calculate the number of charges. This is all about the fundamental properties of charges. This is all about the fundamental properties of charges. Next, that is some auxiliary properties of electric charges are there. So those are an electron, an electric charge. Okay, an electric charge in motion produces a magnetic field in addition to the electric field. See, this auxiliary property, the auxiliary property of electric charge, that is an electric charge. See, an electric charge in motion. Suppose an electric charge it is in motion. Okay, it is in motion. It will produce a magnetic field in addition to means uh, in place of electric field it will produces magnetic field. Okay, instead of electric field it will produces magnetic field. When it will takes place, when an electric charge is in motion. When an electric charge is in motion, it will produces a magnetic field in addition to the, or instead of electric field it will produces magnetic field. Now an accelerated charge radiates. An accelerated charge radiates energy in the form of electromagnetic waves. See, the term accelerated you have heard somewhere else, right? In first PUC, in SSLC, or else. An accelerated charge radiates energy in the form of electromagnetic waves. Suppose a charge accelerates from the one position from, so when it will accelerate, when you give us some kind of charges to this any body, an accelerated charge, when the charge is get accelerated it radiates. Okay, it radiates in the form of electromagnetic waves. It will radiates in the form of electromagnetic waves. These are the two auxiliary properties of electric charges. So dear students, we have discussed fundamental properties of charges, and the second is auxiliary properties of electric charges. Yesterday I have discussed methods of charging a body, that is by friction by rubbing a glass with a wool, or when the two bodies acquire opposite kind of charge due to one body losing an electron to the another body. I have explained in detail. You can watch it. Next, conduction by conduction. Charging by conduction I have explained yesterday. Bringing an uncharged body in contact with a charged body during conduction, the body getting charged acquires a part of the charge from the source, that is charging a body. Next, it is induction. Without touching, induction, bringing a uncharged body near a charged body. So what will happen in this is, say that during induction, the body getting charged. Okay, during induction, the body getting charged acquire opposite kind of charge on its surface close to the charging body. See, I have explained with by giving one example, right? The net charge on the charged body is still zero. However, by earthing, how will we how do you get earthing, or how will you make the body by earthing? Because by touching with the fingers, the charged body can be made to retain one type of charge. It will remain constant with a one type of charge. The charge on the source body remains intact. Intact means without contact. This method is applicable to only conductors. This method is applicable only to conductors. So this can be done by heating a body to a high temperature, by applying a large electric field. In all the above methods, the body regains electrical neutrality over a period of time. I have discussed what about the neutrality, etc. And whether a body is charged or not. If charged, the type and extent of charge can be detected by a device called as electroscope. See whether a body is charged. How do you get whether a body is charging or charged or not? This can be done by how much, or the type or the what extent. What extent of charge can be detected by a device, that device called as electroscope. So by electroscope you can detect, or you can find whether a body is charged or not. Next, the amount of charge on a body can be measured by a device called electrometer. See, you have dual phenomenon here. The amount of charge on a body can be measured. The amount of charge on a body can be measured by a device called electrometer, but whether a body is charged, to detect whether a body is charged or not, we use electroscope. We use electroscope. The what amount of charge on a body can be measured? It can be measured by a electrometer. This is all about the charging process or the methods of charging. Yesterday we have discussed. The next concept, for your syllabus, that is Coulomb's law. Very very important. Coulomb's law. Coulomb's law. It is very important for your syllabus. See, what do you mean by Coulomb's law, and what is the statement? What is the statement of the Coulomb's law in electrostatic? See, the force. Okay, the force. This is the statement here. What is the statement? The force F of attraction or repulsion between 2-point charges. 2-point charges is directly proportional to the product of the charges Q1 and Q2 and inversely proportional to the square of the distance R, that is R, between them. This is called as Coulomb's law. It is very easy. It is very easy actually. By seeing this, F is equal to F here. F is directly proportional to Q1 and Q2 divided by R square. See, what is the statement? The force. Okay, whether it may be attractive force or whether it may be repulsive force between the 2-point charges here, Q1 and Q2 are here. Q1 and Q2 are 2-point charges. Okay, the force of attraction or repulsion between 2-point charges is directly proportional to the product of the two charges. The product of the two charges and inversely proportional to the, inversely means divided by, inversely proportional to the square of the distance. Here you can see the square of the distance r between them. This is called as Coulomb's law. By seeing the statement, by seeing the mathematical expression, you can derive the statement, right? By seeing this mathematical expression, you can easily say it. You can easily say the definition or the statement of Coulomb's law. See, the force of attraction, the force, yeah, force of attraction or repulsion between the 2-point charges, that is Q1 and Q2, is directly proportional to the product of the charges Q1 and Q2 and inversely proportional to the square of the distance r between them. This is called as Coulomb's law. Here, directly proportional. If I want to remove this proportionality phenomenon or the proportionality factor, I need to replace with a constant k. I need to replace with a constant k. Proportionality constant k is nothing but 1 by 4 pi epsilon naught. Here 1 by 4 pi epsilon naught, whose value is equal to 9 into 10 to the power of 9. 9 into 10 to the power of 9 Newton meter square per Coulomb square. See guys, it is very important factor that we need to remember. Here 9 into 10 to the power of 9 Newton meter square per Coulomb square. See, we need to remove the proportionality constant. Instead of writing proportionality factor, I have written k, whose value is equal to 1.1 divided by 4 pi epsilon naught. See, 1 by 4 pi epsilon naught, whose value is equal to 9 into 10 to the power of 9 Newton meter square per Coulomb square. Where another factor we have seen in this, that is epsilon naught. Epsilon naught is called the permittivity of free space. Permittivity of free space, whose value is equal to 8.854 into 10 to the power of minus 12 Coulomb square per Newton per meter square. See, dear students, you need to know about these units. You must remember these units because these are very important in every factor. Okay, these are very important. You need to remember a lot. No need to worry. You can easily take a note. This is all about the Coulomb's law, and also you have learned in PUC first year classes That is dimensional formula of a permittivity, that is, say, Coulomb square per meter, m to the power of minus 1, L to the power of minus 3, and T to the power of 4, and A to the power of 2. This is very important dimensional formula. They will ask dimensional formula also here. Next, here epsilon r is given. What does this indicate? Is a greater than 1. Its value is greater than 1 for a medium other than vacuum. Suppose, for example, for air, its value is equal to 1, then epsilon r is called dielectric constant. It is a dielectric constant and it is denoted by letter K. See, I have said that why I have taken K here. Proportionality constant I have taken here. K is equal to 9 into 10 to the power of minus 9, that is 1 divided by 4 pi epsilon naught. Here, for a medium, epsilon r is a permittivity of the medium, not a free space. It is greater than 1. It is greater than 1 for a medium other than in a vacuum. That's why its value is equal to 1. Therefore, it is a dielectric constant. That's why I have taken K value here. It is denoted by Coulomb. Next point we need to remember is Coulomb's law is strictly valid for only point charges. Strictly valid for point charges in a vacuum. Okay, in a vacuum it is strictly valid for only point charges. Now the presence of a medium. Okay, the presence of a medium, I have said that medium. The presence of a medium modifies the force which is approximately given by, actually if you consider the medium in a, not in a free space, I mean free space actual as well as the medium whose value is going to be 4 pi epsilon naught into epsilon r q1 into q2 divided by r square, when it will be in the presence of a medium, not in the free space. In the presence of a medium, you need to consider both permittivity of free space as well as permittivity of the medium, where epsilon r is called the permittivity of the medium. So dear students, this is all about the Coulomb's law and their important properties and their important dimensional formulas, etc. See, the last concept for today's session, that is Coulomb's law in vector form. I need to explain this. See, Coulomb's law in the vector form. So how do you represent the Coulomb's law in vector form? Let us discuss. See, Coulomb's law vector form. How do you represent Coulomb's law in vector form then? What do you see in the picture here? Coulomb's law of a force between 2 point charges, that is q1 and q2, located at the distances r1 bar and r2 bar, is written as, see, r1 bar and r2 bar, which is written in the form of vector forms, therefore we represent bar at the upper level at the, above those distances. See, Coulomb's law of a force between 2 point charges q1 and q2. Suppose in any area, okay, suppose in any vacuum or in any space, okay, q1 and q2 charges are present. q1 and q2 charges are present. Those distances were equal to r1 r21 from one point charge to the another point charge. Suppose Coulomb's law of force between 2 point charges q1 and q2 located at r1 and r2 as written as F21. Here F21 force will become 1 by 4 pi epsilon naught is similar. Q1 and Q2 are 2 point charges, but R21 square, what it represent exactly? Where F21 is the force exerted on Q2. Force exerted on Q2 and by Q1. The force exerted on Q2 by Q1, and R21. I have said here R21 is a unit vector. R21 is a unit vector towards Q2 from Q1, and R21 is equal to the difference. R21 is equal to, in the vector form it is denoted as R2 bar minus R1 bar. Similarly, force exerted on Q1 becomes Q1 by Q2 becomes opposite to that force. That is F12 bar is equal to 1 divided by 4 pi epsilon naught Q1 into Q2 divided by R12 square R12 cap. So R12 becomes same here, but in opposite form, because the force exerted on Q1 here, not on Q2, Q1 by Q2, it will become opposite to the first thing. It is the unit vector towards Q1 and Q2. Since the above equations are in vector form, and Q1 and Q2 should be used with the appropriate signs. This is all about the Coulomb's law in vector form. In any free space, in any area, suppose the Q1 and Q2 charges are put together, I mean present over there, then the distance between those two charges are represented like this in the vector form. Then the force on Q2 by Q1, it is represented as like this. And similarly, the force exerted on Q1 by Q2, it is represented as like this. This is all about the Coulomb's law in vector form. Some easy points to remember. See, first thing is Coulomb's law. Coulomb's law is strictly applicable to the only point charges. I have said you guys, it is applicable only to point charges. However, in practice, charges are always associated with the matter. It is always associated with the matter which occupy finite value. And in finite volume, the charges are presented anywhere else, okay, in that particular value. So to specify the situation, usually a charge is replaced by a charge of equal magnitude imagined to be concentrated at a single point. So such a charge is called as point charge. What do you mean by point charge then? See, the size of the charged bodies is very small compared to the distance between them. See, point charge. What do you mean by point charge? See, the size of the size of a charged body, any charged body is very small as compared to the distance between them is called as point charges. Or usually a charge is replaced by a charge of equal magnitude imagined to be concentrated at a single point whose value is very small. The size of the charged bodies is very small as we compare to the distance between them. Am I right? These are called as a point charge. Now, the gravitational force. The gravitational force is usually neglected while studying the force between the electric charges, because why? Because gravitational force is negligible compared to electrostatic force. As compared to electrostatic force. See, the gravitational force is usually neglected by why? Because gravitational force is negligible compared to electrostatic force. So the electrostatic force is dominant here as compared to gravitational force. Therefore, its value will be neglected. And the ratio of electrostatic force of repulsion to the gravitational force of attraction between two electrons separated by 1 meter is value is equal to 1.7 into 10 to the power of 10 to the power of 43. Okay, its value will be 1.7 into 10 to the power of 43. Whose value? The ratio of electrostatic force of repulsion to the gravitational force of attraction, okay, between the two electrons separated by 1 meter, is value is equal to 1.7 into 10 to the power of 43. Next, the relative permittivity epsilon r of a medium is nearly constant. The relative permittivity epsilon r of a medium is nearly constant Epsilon constant means 1. Epsilon r depends both on the property of the medium and the magnitude of the charges. See, the relative permittivity of the medium r, I have said its value will be constant, and epsilon r depends both on the property of the medium and the magnitude of the charge. And epsilon r is only a number and has no units. It's only a number. It has having only no, any it has no any units. Epsilon r is also called as a dielectric constant. Why it has no any units? It is a constant value. It's not any variable value. It's a constant value, or that is dielectric constant value. It is therefore it is having no any units. It's just a number. Next, the unit of charge is coulomb. In the first class, I have said you that the unit of charge is coulomb. See, next, the charge on an electron is equal to minus 1.6 into 10 to the power of minus 19 coulomb. Next, the 1 coulomb charge has 6.25 into 10 to the power of 18 electrons. 1 coulomb of charge, how many electrons? 1 coulomb of charge is equal to 6.25 into 10 to the power of 18 electron points to be remember. Next, a test charge is a hypothetical infinitesimally small charge. I have said in a point charge. A test charge is a hypothetically infinitesimally small charge. You can't even imagine the smallness of that quantity. Okay, the test charge is a hypothetical infinitesimally small charge kept at a point to evaluate the electric field at that point without disturbing the field. Okay, a test charge, it is all about the test charge, is a hypothetical infinitesimally small charge kept at a point to evaluate the electric field at that point without disturbing the field. This is all about the test charge. So, dear students, in this today's session, I have discussed about the fundamental properties of charges. That is, charge is conserved, charge is quantized, charge is invariant, and charge it is a scalar quantity and it is a additive. Like charges repel each other and unlike charges attract each other. Next, coming to the auxiliary properties of electric charges. All electric charges in motion produces a magnetic field and in addition to the electric field. An accelerated charge radiates energy in the form of electromagnetic waves. And methods of charging by body. Next, coming to the Coulomb's law, I have explained everything. This is very essential for your syllabus, for your preparation. So I hope so you have understood the concept very well. And in the upcoming section, we will discuss further concepts related to your syllabus. So I hope you got the point. And let us wind up the session today. And thank you everyone. Please don't forget to subscribe our channel. Thank you.